Get through the notes over this concept of independence today. Tomorrow we'll have some practice problems with it. The reason I'm spending a lot of time on this is one, it's actually a fairly important, big, real-life concept, okay? And two, often one of the most misused and misunderstood statistical concepts. Everybody with me? Okay. So you guys, overall, if I roll a dice, what's the probability I roll a 1? 1 out of 6. Okay, great. Now, what if I roll the dice twice? The first time I got a 1. What's the probability I get a 1 the second time? Still 1 out of 6. No matter what I do on the first roll, what's the probability I roll a 1 on the second roll? 1 out of 6. Stays the same the whole time, yeah? This is independent. Okay, so the rules of independence are that the probability of something doesn't change no matter what has already occurred. Okay. All right, different probability event. This time what we're going to do is I'm first going to have you draw a card out of the deck, and then you're going to roll a dice, yes? Everybody good? What is the probability you roll a 1 given that you picked a red card? It's still 1 out of 6. Everybody good? Okay. Now, tree diagram of the first one. You rolled a 1 or not a 1. And it was 1/6, right? And then given you roll a 1 on the first one, it was still 1 out of 6. Yeah? Okay. So conceptually for independence, what's important is that these probabilities on the second set of branches stayed exactly the same. Everybody good? What would the tree diagram look like for the second one? Well, the first thing that would have happened is drawing a red card or a black card, right? What's those probabilities? 50 and 50. And then you either rolled a 1 or not a 1. Notice again, these probabilities didn't match, but these ones did, yeah? And is this one independent? Yeah. Okay. The reason I'm pointing this out is a lot of times people compare, when I say that people make common or have a lot of misconceptions about independence, is they believe they could be comparing what card they drew to whether or not they rolled a 1. And that's not what independence is about. If two events are independent, that means what happened at first doesn't change anything about what's happening second. Okay? And in a tree diagram, we would see that the branches for the second set match each other. No matter what happened in the first event, the branches in the second event stayed the same. Whereas that drug testing trial thing that we did the other day was not independent, because if you knew somebody had taken drugs, they were more likely to test positive, yes? Okay? That would be dependent events. Now, there are some independent and dependent events that are very, very obvious and some that aren't, okay? And so as we go through these, if we're trying to decide are two events dependent or independent, what we're really asking ourselves is there a relationship between the two variables? Okay? Now, the formal definition of independence is that the probability of A is equivalent to the probability of A given that B has occurred. Now, if my events have different letters, that's different. We just use different letters. So what if I said the probability of B Well, that means that I got to find the probability of B given that something has occurred. And I used A, but it would be any of them, okay? And it doesn't matter which set. You can either choose this one or some version in between. It doesn't matter. But we need to show the same probability twice. Once given something has occurred and once that it hasn't occurred. So in this particular case, do you guys think there might be a relationship between people having a driver's license and people having a job? Why? If you can get your driver's license, you can get a job for sure. Like a 10-year-old has neither, right? Also, like if you have a driver's license, it opens up where you can get a job, so that you don't need your driver's license to get a job. However, it would certainly help if you have a much larger radius where you could go in order for your job. Also, if you have a job, you can pay for gas, you can pay for car insurance, you can, etc. Yeah? Okay. So, here's a two-way table of a bunch of students. If I ask you right now, you guys, what is the probability somebody has their driver's license, what would you say? 28 out of 50. You took the license column over the total column. I'm not very smart, guys, but I know I can do something out of 50 into a percentage pretty easily. All right. Now, what if I know that person has a job? Now, what's the probability they have a driver's license? It would be 20 out of 31. It's something I want to point out. You guys? Do you guys see how the fractions were formed in the exact same way? Both of these fractions are this column over this column. We good? So I'm not like comparing the 28 out of 50 to the 31 out of 50 because then I'm comparing two different things. Both of these are the probability of having a driver's license. Everybody good? 21 out of 31 is probably about short of 0.6, so 0.65 maybe? Can someone help me out?
0.645.
It's close. Okay. So does there appear to be a relationship here? Yes? Why?
More people have jobs more people have their license that have a job.
Okay. I'm going to say that.
Yeah, you can.
I don't love the language you use, but your thinking is correct. You guys, if I were to say people who have a job are more likely.
But this has a job and female.
I know, but that was because I changed it. Okay. If you can write this statement that somebody is more or one group is more or less likely than the others, then they are not independent. We say those variables are associated. Is everybody with me? Is this a big difference between the two? No? Can you guys do me a favor? Find the probability that somebody has their license if they don't have a job. What did you guys find?
42%, or 0.421.
It was 8 out of 19. All right, so if I compare these two numbers, is there a big difference? That's a huge difference. So how come this one wasn't as big? Well, because this is, it's not the midpoint of these two, but it's kind of like the average of these two, accounting for that the groups aren't the same size. Okay? Everybody good? And I can compare, if when I'm trying to make this decision, again, notice that every single one of these fractions we're comparing are the same relative column to total column. Do you guys see what I'm saying there? Okay? And it's the fact that the proportions aren't the same throughout the table that makes that happen. Likewise, instead of comparing L given J, I could have easily answered the independence question by finding the probability of J and the probability of J given L. Like, there's nothing that says I had to do it this way. I could have also done this. They would look different. They would get different answers, but they still wouldn't be the same number. Everybody good? Okay. Here's one that I would like you guys to try. I'm sorry?
We're playing people with jobs with no driver's license.
Exactly. But we don't talk about individuals, right? Like, we talk, statistics isn't about individual observations. It's about the collective. Give this one a shot. You okay? for right now. If they are different, they are different, not independent.
Because they're different.
For right now. So the question becomes, it's a much bigger question than you guys know that you're asking. In that it kind of depends on, is it a sample versus a population? That's one of the important things, right? So if a sample, if the proportions of a sample are close, we would probably be iffy about saying they're independent or not independent, making that conclusion. But if it's of a population in itself, we can say that there are slight differences. For right now, all you got, like, if the question is specifically, are they independent? Then any difference is a difference. But you are right in thinking that how different do they need to be, right? Like that's not a bad thought process that you're having, but it's not a, right now don't worry about it. I'll tell you when you need to worry about that. And there's a very specific process we follow to make like that broader conclusion where we look at are they actually far apart enough for us to say it's for real. We're just not there yet. It won't be until March. That's what you're learning in March. We doing okay so far? All right. I do want to point out a couple of things. I'm going to tell you how I would grade this if this were a free response question, which, by the way, this is a very common format for a free response question. I know of at least 3 different times it has been asked just like this on the AP exam, which is a lot for any one specific kind of question. Okay? In order to earn an E on part A, you would have been expected to have both the fraction and the decimal. Or if you turn this into a percentage, that would have been fine, but you needed to have both. So if you only had the 0.375, you would earn a P on this section. Does everybody understand what I'm saying here? The reason I'm pointing this out is there's several topics as we're going to get going here with probability. There are many topics where students feel like they shouldn't need to show their work, so they don't, and then get mad. Everybody good? Your rule of thumb should be, do not write down a number that I didn't give you unless you tell me where it came from. Everybody good? Same idea here, you needed the fraction. Did we get these probabilities correct? Okay. Great. Now.
Do you need the actual probability parentheses thing?
You don't, but I would.
Okay.
So the next thing is, and this will be a good example of it, okay? Down here, you need to have a yes or a no about are they independent or not. Okay, so they are not independent. And you would need to show not just what those probabilities are, but state somehow that those probabilities are not equal. So, in the past, students would say the probability of P equals 0.375, the probability of P given F is 0.444. So they are not independent. And that would not be sufficient to just state the probabilities. You have to say, what are you looking at between these two numbers that made you decide they are not independent? It's the fact that they are not equal. Okay? And you would either write this or this, right? But if you wrote this here, you would need to have it up here so they know which probabilities you're referring to. What questions do you guys have? All right, turn the page. We're going to just do the top of the next page. Tomorrow, like I said, you're going to have some practice free response questions. I'm going to let you guys look at this for a second and strategize. What strategies are you thinking we should do?
Two-way table.
I would build a two-way table here. Do you have to build a two-way table? No. Did anybody try to do a tree diagram? Or want to do a tree diagram? Perfect. Okay, so if I'm doing a two-way table, I have two variables. Did the people read USA Today or not? And did they read the New York Times or not? Tell me everything I know.
Read the New York Times.
So that would be my total for the New York Times. What does that mean the total for not reading the New York Times is?
75.
What else do we know?
45%.
45% read USA Today. So 55% do not.
10% read both.
Seems to be working out. All right, now, if we want to know if it's independent, we need to find two probabilities. Which ones do you think we need to find? You have two sets of options here.
Probability of reading the New York Times.
Okay, if that's the one I'm finding, I need to compare that to the probability of reading the New York Times, given that they also read USA Today. So let's see, that would be 0.25 and 0.1 over 0.45, which is 0.22, repeating, I think.
Yeah.
So are they independent?
Yes.
Are they the same? So are they independent?
No.
They have to be the same number. In order to be independent. Are they close? Yeah. And in broad perspective, maybe. But for right now, for our purposes, unless they work out to be the same thing, they are not independent. Okay. I do want to talk about one more thing. Kind of make a connection for you guys here. Do you guys remember talking about the probability of A and B is equal to the probability of A times the probability of B given A has occurred? Is everybody good? Okay. Well, if the two events are independent, so this next part only applies to if independent. The probability of A and B would equal the probability of A. Well, if they're independent, B given A is equivalent to just B on its own. And the reason I'm pointing this out is using this rule would be a lot easier on this particular problem Because we could say, well, we know the probability of A and B was 0.10. We were given the probability of A was 0.25. The probability of B is 0.45. And if I multiply those out, I get like 11 and some change. I think we get 0.1125, I think. I'm doing that from memory, not from brains. So are these two things equal? So it's just a different rule for checking independence. Whereas if they were independent, it would work out that both of those things ended up being the same thing. Okay, I'm done for today. Tomorrow we're going to do more practice.